Alrighty, guys. Good morning, and welcome back again to College Algebra today. Today is, I believe, Wednesday, the 19th of November. And as you see, I am out of the building today. I'm homesick. I caught some sort of nasty bug on Monday morning, and it's not shaking out just yet. So, figured I'd stay back and avoid spreading it around. In the meantime, I have for you guys a video lesson that I've recorded for our second bout of the material in our last unit of study on polynomial functions. Today we're going to talk about finding the roots or the zeros or the x-intercepts or the solutions of functions that fall into this sort of broad family of functions that we refer to as polynomials. There's a lot of methods that we're going to borrow from what we saw so far in Unit 3, especially the idea of like factoring and applying the zero product property. But there's also going to be some other edge cases that we're going to consider and think about, and how that's going to connect back to what we saw with like the fundamental theorem of algebra and the idea of complex numbers. So there's a lot of things that are sort of coming together here from what we saw in Unit 2. As much as possible, I'm going to try and work it out to where we use like graphical approaches to sort of verify solutions, but also connect it back to more algebraic methods, especially the zero product property and the fundamental theorem, to understand when we should get a certain number of solutions and where the rest of them might be hiding, and some of the different strategies we can use to pin them down. As we get rolling into our lesson for today, please make sure to leave your phone in the correct assigned slot here while the sub is in. Other than that, we'll get rolling here with our warm-up in just a moment, where I want to talk a little bit more about a couple examples from the practice in 4.1. For 4.1, we have two functions, f of x and g of x. We are trying to determine two things. We're trying to understand the end behavior of the function. So what is it doing as we go way to the edges of the graph on the left and the right? But we're also trying to figure out like what kind of symmetries they might exhibit. So whether they are even, odd, or neither, perhaps. So what I want you to do real quick is maybe try graphing these. Maybe try like Desmos or a graphing calculator if you have it. Try looking at a graph for these guys and seeing what you notice. I tend to find pulling answers for this from like Desmos is a really, really fast, efficient way to do it. What I'm going to highlight here in the video is the more algebraic side of the problem. How we can sort of verify this without necessarily having to graph it, but it's a useful fallback. So I want you to start there. Graph it, think about the end behavior, and then think about the types of symmetries you might notice and observe. We'll sort of play it by ear from there. All right, so for each of these functions, we are interested in determining two things. We want to know about their end behavior, and we want to know about any sort of symmetries that they're going to exhibit. I kind of chose deliberately a couple of nasty looking ones from the later part of assignment 4.1. If I'm thinking about end behavior, essentially what I'm looking at is the graphs go way out to the edges, is whether they're going up or down, or they go in the same direction or different directions, right? And we often explain this in algebraic notation with using this sort of limit notation, where I do like the limit as x goes to infinity of my function is something. Then on the other side, right, the limit as x goes to negative infinity, way to the left of my function is some result. One thing that often helps me is to double check that my functions are written in decreasing orders of powers. In standard form, this guy for f of x would look something more like 4x to the 13th minus 2x to the 9th plus 3x to the first in that case. I like to reorder the terms because what I'm going to notice here is that from our last lesson, we made the observation that the highest powered term ultimately calls the shots as far as the end behavior is concerned. And what we're often looking for here is like the degree of the function, the power that it's exhibiting, and whether that number is even or whether that number is odd. What I'm going to notice here is that I have an odd degreed function. So it's like a 13th degree polynomial. Anytime I see that that leading degree is an odd number, I know that the end behavior is going to split. And then what I also want to think about is the number a that's multiplied onto it, what we call the leading coefficient. If that number is positive, I'm going to get the usual end behavior for odd powers, which is right and up, left and down. If it turns out to be negative, I've got to sort of switch it the other way around, right? It's going to reflect over the x-axis and change things up a bit. So what I'm going to see here is that if I'm going with the full analysis, if I'm going with the full like limit notation for the end behavior of my functions, we use the keyword limit to say that we're talking about end behavior. And then we say for the input variable, in this case x, it's got to go either to the right, so towards positive infinity, or it's got to go way to the left on the graph towards negative infinity. We have to be very careful to specify which direction we're going, because you might get very different answers for odd-powered functions, especially, depending on which way you go. Now, as it goes way to the right, I'm going to see eventually that the graph goes up forever to positive infinity. As I go way to the left, I'm going to see that this graph goes down forever towards negative infinity. And I've got the end behavior for that more or less figured out. I can do the same thing for my function for g of x. Nice thing about this is that it's already written in standard form. What I notice here is that the degree of my function is 6. So it's a 6th degree polynomial. Polynomial meaning there's just a bunch of terms involved in the full equation, right? Given that 6 is an even number, I know that this is going to exhibit like up, up, end behavior. At least that's what it usually does, right, for an even degreed function. The fact that a is a negative 2 is going to sort of switch things up. So instead of going like up and up eventually, what I'm going to see is that the graph at the end of the day is going to go like down and down. So if I want to capture the end behavior for this, I got to make sure that it matches in the answer. That's kind of first step, right? But I got to make sure to catch which way in particular it's going. So I've got two limits. One is x goes to positive infinity. Another one is x goes to negative infinity. We're talking about the function g of x. So what I have to say here is that if it's going down forever, each of these limits is trending towards negative infinity. And we've got our final answer for, say, the end behavior of the function. I would say that's kind of the more familiar part. That's definitely the thing that you guys have seen from Algebra 2. The idea of like symmetries, of evenness or oddness of the function overall, that's kind of the new thing, right? And there's sort of two conditions that we've seen for how to check whether this is going to work in an algebraic context. What we've seen is that a function is even if it exhibits a sort of like over the y-axis symmetry, right? So if I were to draw like, say, a quadratic as an example of an even function, what I'll notice is that there's like a mirror image coordinate on one side of the y-axis that maps onto the other if I flip it over. It goes right back to mapping on itself, right? What you'll notice though is that the first coordinate over here is like x comma y. The coordinate over here on the left-hand side when I map it over is at negative x, but the same y value. So we sort of created this condition that said, okay, well, if I have my function f of x and I switch the input to being a negative number, it should yield the same y value, right? So f of negative x should be really no different than f of x. And that's sort of like the way to check whether a function is even or whether a function is odd. On the other hand, sometimes we see that instead of like a reflective symmetry, something exhibits what we call a rotational symmetry. And in particular, what we're looking at here is a rotational symmetry that goes about 180 degrees around. So a function that's kind of a classic example of this looks a lot like a propeller, is like the x to the third power function. What I'll notice is that if I focus on a coordinate in the upper right quadrant, like x comma y, if I sort of rotate that 180 degrees around, like turning a steering wheel, he ends up in this lower left quadrant where now he's negative x, but he's also negative y. The condition that we ultimately saw for that is that if you have a function and you give it a negative version of the input, you should get the same value as the output, but it's going to be the negative version of it. So the condition to check for that is whether f of negative x is negative f of x. The original y value just switched, positive to negative or negative to positive. So those are the conditions that I'm kind of running through with each of these functions. Notice in both of them, I have to give it a negative input and I just have to see what happens. So I'm sort of testing by giving a negative x to these and then simplifying to see what's ultimately going to happen. So let's say that I'm working with f of x. I'm going to deliberately feed it a negative x, and I want to see what happens. So I've got 3 times negative x minus 2 times negative x to the 9th plus 4 times negative x to the 13th power. Now, if I do 3 times negative x, that's just going to look like negative 3x, right? If I do negative 2 times negative x to the 9th, I'm probably going to have to figure out that power term first. A negative number times itself 9 times in a row is still going to come out overall negative. So this negative x to the 9th is going to look like negative x to the 9th. And I know that doesn't seem like I did anything different, right? But you can think of that as like -1 times x to the ninth is equal to 9 on negative x. Now, that -2 is going to sort of throw things off, right? -2 times -1 is going to make that look like now plus 2x to the ninth. And same thing for 4 times -x to the 13th, right? If I think about -x to the 13th power, well, -x to the 13th is an odd number of multiplications, so it's still going to look negative. It's now going to be -1 times x to the 13th. And when I do that -1 times 4, what I'm going to get there is something like -4 x to the 13th. Now, I want to compare that against the original equation, right? What I'm noticing is that when I compare to the original, I started with 3x, but now it's -3x. I started with -2x, now it's plus 2x to the ninth. And I had plus 4x to the 13th, and now I've got -4x to the 13th. So it's the exact same function, it's just everybody's got their signs switched. So what I'm noticing here is that when I give it a negative input, it's like negating the original outputs. F of -x is the same thing as negative f of x. So f of x in this context turns out to be an odd-powered function. It's met that condition. And what you'll notice is if you graph it and like grab the top and the bottom and turn it 180 degrees on the graph, it maps right back onto itself perfectly. Now, let's maybe try g of x. G of x is a bit of a doozy, right? It's a long function, but I'm doing the same thing. I'm going to deliberately feed it a -x. I'm just going to see what happens. Now, I've got -2 times -x to the sixth plus 3 times -x to the fifth minus 2 times -x to the fourth. See where this is going to get tedious, right? Plus 5 times -x to the third minus 122 times -x squared plus 35 times -x. And then finally I got my constant at the end that's just -90, right? Now, any even power on these variable terms is going to switch that -x to looking like a positive x. So I can kind of speed this up by saying, okay, -x to the sixth is going to look like -x to the fourth, it's going to look like -x to the second. They're all going to switch back to being positives multiplied by their leading coefficient, right? So -2 times -x to the sixth is going to stay looking like -2x to the sixth. -2 times -x to the fourth is still going to look like -2x to the fourth. -122 times -x to the second is still going to look like -122 x to the second. Now I can deal with the odd power terms, right? A negative number to an odd power is still going to be negative. So plus 3 times -x to the fifth is now going to look like -3 x to the fifth. Plus 5 times -x to the third is going to look like -5 x to the third. 35 times -x is going to look like -35x, and I've still got my constant on the end that's just -90, right? Now, what you'll notice is that some of these terms are exactly the same as what we started with for g of x, but some of them aren't, right? Some of these are identical, and some of these are very, very different. In particular, what I'm noticing is that I go from positive 3x to the fifth to negative. I go from positive 5x to the third to negative. I go from 35x to -35x. So it's definitely not an even function, right? I don't get the exact same thing out of this. But it's also not an odd function, because if it was an odd function, everybody would have been the opposite sign. So if I see that neither of these conditions have been met, the graph that we were working with here has neither reflective nor rotational symmetry. And you'll see that if you graph it in Desmos, you'll see this really complicated looking wiggly function. You can't reflect it over the y-axis to map back onto itself, and you can't like rotate it like a steering wheel 12/6 and get it to be mapping onto itself that way either. So a lot of polynomial functions are going to be neither. Some of them, it turns out, do have this reflective symmetry, this oddness. Some have, rather the reflective symmetry is evenness there. Some of them have like a rotational symmetry, the oddness, but most of them are going to be neither. So it's not exactly a surprising result. It's pretty common. So that's what we opened up with for our notes so far with polynomials. Where we're going today is kind of the attach point for what we're going to see with Unit 4, going back to our knowledge so far from Unit 3, where we're talking about like the fundamental theorem of algebra, We're talking about roots of functions and ways to arrive at them. Talk about how to get the zeros, the x-intercepts, the solutions, and also what happens sometimes when you don't have enough of them, right? Where you get those complex or imaginary numbered roots. Our first quiz is going to be November the 21st to the 24th on these two topics. So we'll see some work with like evenness versus oddness. We'll see some work with end behavior, but we're also going to focus a little bit on the intro to solving. And this will be something that we carry off through the rest of the unit, so we'll get lots of practice with it. 4.3, we're going to continue working with some of the important locations and behaviors of polynomial functions. Then as we go into Thanksgiving break, we're going to talk about the rational root theorem. Kind of a nice to know in the sense that it helps guide us into how to find some of these different roots when we can't necessarily factor to get them. And then we'll start wrapping things up with graphing and finding equations of polynomials, and that'll kind of reinforce an idea that we talk about a little bit here that we refer to as multiplicity. So our goal for today is to recap and review methods for solving quadratics that we found useful, especially by factoring and applying the zero product property. But we're going to take those, we're going to kind of graduate up a level and use them in maybe more sophisticated scenarios where instead of maybe just 3 terms, there's like 4 terms. Or even in scenarios where I've got 2 terms, there's kind of a more like interesting factoring approach to take there with like the sum or the difference of perfect cubes. So a lot of this is going to feel familiar, but there's also going to be some new extensions based off of what we've seen in the past so far. So we started off in Unit 4 by talking about the connection between like power functions up to general polynomials. The kind of the archetypical power functions that we've seen so far are things like x to the second and x to the third, which are known as quadratics and cubics. We saw back in Unit 3, though, that most quadratics aren't just a single term to the second. There's all sorts of stuff attached onto it. And when we attach those extra terms onto that initial term, that's what creates something that we refer to as a polynomial function. So all quadratics, all cubics, all fourth degrees, all fifth degrees, all sixth degrees, there's like an infinite number of different subclasses of these general polynomials. This is, I would say, probably the biggest family of functions that we're going to work with in an algebraic context. But essentially what it is just a bunch of power terms added or subtracted together to get more and more sophisticated behavior. And our goal today is to try and find solutions or roots or zeros of them. So oftentimes we're going to start in standard form, and what we're developing an intuition for today is how to convert that from standard form for polynomials into something kind of like factored form here, where once I have it in factored form, I might be able to think, okay, how do I find the roots where the graph is intersecting the x-axis, kind of like quadratics? And just like we saw with quadratics, oftentimes that's going to involve a process of factoring strategies and then an application of what we're going to see with the zero product property. Now, what we've got so far in our understanding for factoring is that there's kind of like 3 scenarios that we often find ourselves in these types of problems. Sometimes you have something with 2 terms, where often we try and factor it with the difference of perfect squares. Sometimes you got something with 3 terms, so that's where we use like the AC method or the X method. And every once in a while, we're in a scenario where we're trying to factor something with 4 terms, right? And that's where we apply factor by grouping. That's still going to apply here. That's going to serve actually as kind of the general approach across the board with polynomial functions for how we want to try and tackle them. Once we're able to factor everything down, if we can set it equal to 0, we can then solve it by using this sort of zero product property, right? If I say one thing times another is nothing, you know for sure one of the things is nothing, and you kind of work it out from there in separate processes. So if x minus a times x minus b is 0, either x is a or x is b, and they're both valid because it creates the equation 0 equals 0, which is a true statement. We got to get all of them though, right? And that's kind of where it starts to get interesting. Now, in the notes for 4.2, I want to point out here that they start with what's, in my opinion, the hardest problems right off the bat. I don't want to do that. In fact, I'm going to kind of go almost completely backwards in the notes, where I'm going to start kind of in the middle. I'm going to work forwards a bit to the very last couple of examples, and then I'm going to jump back to the first 2. So all of these are examples that you'll find in the paper copy of the notes. I'm just going to warn you ahead of time, I'm not doing it in the same order that it's presented there because the first couple are actually really interesting and challenging, and I want to kind of leave that for last. I want to start with maybe more familiar ground first and work up to those. So a little later, kind of in the middle of the notes, they give us a cubic polynomial function, f of x here. F of x is 2x to the third minus 5x squared plus 18x minus 45. And our goal is to find the zeros of that function, find where it hits the x-axis, right? You can totally verify that by graphing. You can go to Desmos or a graphing calculator, you can punch that in, you can compare it against the line y equals 0, and you can find every single one of them graphically. So there's no excuse to not know what the solutions of the function should be, at least in the real numbered plane. Now, what we want to talk about here is how do we do it algebraically, right? How do I verify those solutions by working it out step by step using algebra? And then we'll sort of cross compare, right? I'll show you the graph in Desmos, compare it against the algebraic work, and we'll use it to confirm that these strategies actually do apply. For this function, I'm going to notice that I have 4 terms. If I've got something with 4 terms, the strategy that I want to apply here is factor by grouping. The way factor by grouping works is that you focus on each pair of terms, the first 2 and the last 2, and you're trying to track down a GCF that you can take out of each of those so that the things that get left behind in parentheses match. They're exactly the same. If you can do that, what you'll see is that you can then sort of finish the factor by grouping and create 2 linear or quadratic factors that you can then try and find the solutions for. So as an example, let's say I want to focus on the first 2. If I got 2x to the third minus 5x squared, I notice that I can take an x squared out of both of them, and it's going to leave behind a 2x minus 5. If I look at the next 2 terms, 18x minus 45, I've got to find something that I can take out of both of them to leave behind 2x minus 5, and that happens to be a positive 9. So once I've spotted the GCFs that I can remove, and those factors inside parentheses are matching, then I can say, okay, the terms outside parentheses are going to form one factor of the factored form, and the things already inside parentheses, they're going to form the other factor. So now I've got f of x is the quantity x squared plus 9 times 2x minus 5. Now, as I'm looking at each of these factors, something that I'm always asking myself is, can I go any further, right? I see an x squared and I see a 9, so my mind automatically goes, hey, maybe difference of perfect squares is going to work. But what you'll notice is that that's not a difference, right? That's x squared plus 9, not minus 9. So unfortunately, that is as factored as it's going to get. We're unable to take that any further than where it is. So this is where officially we're going to start to think about the zero product property. Now, to use the zero product property, we want the function equal to 0. So oftentimes we have to set f of x, the dependent variable, equal to 0. So if x squared plus 9 times 2x minus 5 is 0, then that means either one of those factors is 0, and I should go from there to try and solve it out, right? Now, let's say that x squared plus 9 is 0. If I want to solve for x to the second, I could subtract the 9 and then take the square root. But what you'll notice here is that you're not going to get real numbered solutions out of this. There is no number times itself that's still negative. So even though the root of 9 is positive minus 3, the root of negative 9 is not just plus minus 3, it's plus minus 3i. It's in a whole different dimension, but there's 2 solutions there, right? Now, if I'm focusing on the other factor, that 2x minus 5 is 0, I can add the 5 over and then divide by 2, and I'll get my other solution is about 2.5. So if I'm thinking about this purely algebraically, I've got a mixture of types of solutions, right? I've got one real solution, and I got 2 imaginary solutions. I want you to look at the original degree of this problem, though. If you look at f of x, and you look at the leading degree, how many solutions would we expect for a cubic function? Reasonably, we should get 3 of them, right? So even though 2 of them are imaginary and 1 of them is real, algebraically, we've accounted for all 3 of them. We know exactly what they are and what their types are. Now, I'm going to pause the video here, and I'm going to switch over to Desmos real quick and kind of show you graphically how to confirm the real valued solutions. Confirming the imaginary solutions is not so simple, but I want to make sure to show you like an analog process that you could use to verify that 5/2 really is an answer. So as we switch gears and we move in a different direction, right? I found for f of x, currently shown as this red graph, the one that we're working, that it had 1 real solution and it had 2 imaginary solutions. The real solution that I got was something like 5/2. And what I'm interested in doing with the graph of this function is trying to verify that, right? Now, I know that a function is going to have a solution when it equals the y value 0, which is the same thing as saying that it's going to be punching through or touching the x-axis in some fashion. Now, I definitely see a place on the graph over here where that seems to be occurring, As I zoom in a little bit closer, what I'm going to notice is that that answer is x equals 2.5, which is the same thing as 5 halves. So graphically, if I was using like only this strategy, I could find the real solutions to this cubic polynomial. But what you'll notice is that you'll never be able to pin down the imaginary ones, right? The reason you can't find the imaginary roots on the Cartesian coordinate system is that the x and the y values are both real numbers. If you wanted to find the complex or the imaginary roots, you would have to introduce a third dimension coming out of the screen or into the screen for the imaginaries. And you'd see instead of a line that you get a surface that's like bending and curving to sort of hit different axes in this new number system. It's well beyond the scope of a high school algebra class to try and graph that in like 3 dimensions there, like a weird like Cartesian Gaussian cross. We're not going to be interested in doing that kind of thing. So a graphical solution will definitely tell you the real solutions. You just got to be careful because sometimes there are more than that. And when they're imaginary, we have to be able to work it out algebraically to find them. So as we come back to our notes, one thing that I want to continue to highlight here that we talked a little bit about in our lesson for, I think, 3.4 when we introduced imaginary numbers, is that the fundamental theorem of algebra should still apply, right? Cubic functions in general should have 3 answers. What we're going to extend that to say is that sometimes they're real and sometimes they're imaginary. We should get 3 of them, though, and we shouldn't be missing any. So we got to know how to account for them when they do appear to be missing. Here's another one. Here is f of x equals 4x to the fifth minus 8x to the third. I see 2 terms, so maybe I'm tempted to maybe think in the direction of like a difference of perfect squares. But before I do that, one thing that I always want to highlight is that when you're factoring, I always recommend starting with a GCF. It's going to make your life a little bit easier later on down the line. Because usually if you take the GCF first, you're left behind with something a little easier to factor. Oftentimes when it's available, you want to take it right off the bat. So what you'll notice here in this problem is that there is a GCF. Between 4 and 8, the GCF is 4. Between x to the fifth and x to the third, your GCF is x cubed. So if I factor that GCF of 4x to the third out of both terms, I'm left with this kind of scenario here, right? I've got 4x cubed times x squared minus 2. Now, again, inside parentheses, I want to check to see if I could go further. It's really tempting here to think, okay, can I do the difference of perfect squares now? X squared is definitely a perfect square. You could use the strategy on that, but you'll notice that 2 is not really a perfect square. You can't write it as like something times itself, at least not easily, right? So even though I want that strategy to happen, it's just not going to go. So sometimes you'll see that doing a GCF and then another strategy is very much the direction you want to move in. Sometimes you'll see that the GCF is really the only thing you can do, and then you're ready to go straight to the zero product property. So here what I'm going to do is set my function to be equal to 0. 0 is either equal to 4x to the third, or it's equal to x squared minus 2. Given that I don't know which one it is, I check them both out independently. And I try and track down all the solutions in both cases, right? Now, if I think about, say, 0 equals 4x to the third, I want to isolate x. So I might start by dividing both sides by 4, and this is nice, right? Because 0 divided by 4 is still 0. But then I got to do the opposite of cubing, which is cube rooting. And the cube root of nothing is still nothing, because nothing times nothing times nothing is nothing. So it appears that I have a real solution at x equals nothing, right at the origin, right? If I look at the other factor where x squared minus 2 is equal to 0, I can add the 2 and then take the square root. So I get 2 solutions out of that, the positive and the negative version. But it's some crazy irrational decimal, right? So I usually leave it in this format. It's a little bit cleaner and it's exactly right. There's a bit of a problem though. If you look at f of x and you think about the highest degree term in the lead on that one, it's a 5th degree polynomial, which means by the fundamental theorem of algebra that we should expect 5 solutions. Now, I didn't do anything here to insinuate that there's like imaginary or complex roots, right? I didn't take a root of a negative anywhere in the process. I used inverse operations. Everything's coming up to be real valued solutions. So what gives, right? Something's not quite right. Now, I want to maybe highlight this bit on the left-hand side where we were working with like x to the third equals nothing. One way to sort of explain why you're only getting three answers when you should have five is to say, okay, x to the third is really like x times x times x, right? So one particular way that you could approach this problem is to say, really, you've got like 4 times one factor times another factor times another factor times x squared minus 2 is equal to nothing, right? And what you'll notice is that those three independent factors of x, they all yield the same solution. They all say that x is nothing, but they say it 3 times. They're repeating themselves, right? And when you look at this factor x squared minus 2 is equal to 0, that gives you two distinct solutions where it's the plus minus root of 2. So if you have a variable to a power, and you're getting a real valued solution out of it, sometimes it's going to give you 1 or 2. Sometimes it's going to give you a whole bunch of them. And when we refer to that as a factor giving multiple repeated answers, we call that multiplicity of a solution. So you'll notice that there's only 3 distinct solutions. It turns out that one of those distinct solutions, x equals 0, shows up 3 times in a row. And we usually don't write that, right? We say like x equals 0 with multiplicity 3, or we say x equals 0 is a distinct root, right? But we have to track the fact that it's repeating to make sure that the fundamental theorem of algebra still works. So sometimes you'll see that happen. It's not a bad thing. If you get like x to a power equals nothing, you know you're going to get repeated roots that are exactly the same. You just want to track that there's that multiplicity issue that can sometimes happen. So everything's accounted for. The fundamental theorem of algebra is still holding. Nothing's gone amiss yet, right? Even though initially it looked a little suspicious. Now let's carry on from there, right? Let's say that I've got f of x equals these 3 terms, adding or subtracting together. If I see something with 3 terms, I'm usually tempted to say, let's do the AC method, right? But what I want to think about here first is a GCF. Notice that all 3 of these terms have an x in common. So I can factor an x out of everybody, but that's really about it. So when I take that GCF of x out of this, I'm left with something in parentheses that's got 3 terms. So I'm probably thinking, okay, let's try AC method. But you're probably looking at this and going, well, wait a minute. It's not a quadratic. The AC method is something that we reserve for solving quadratic functions, right? So how are we supposed to use the AC method when it applies to quadratics when it's not quadratic? It's a variable to the fourth, and then a variable to a second, and then a variable that's a constant. That's a really good question. A lot of people get tripped up on this approach. And one way that I like to look at this is by sort of rewriting this with a clever substitution of variables to sort of reveal the quadratic pattern again and use that AC method on something else that's maybe a little more comfortable. Some people like this approach. Some people absolutely hate it. I'm going to show it to you for the case that maybe you enjoy this and you're okay thinking about it this way. But as we come back, I'll maybe show you the other way to work it, where essentially you're doing the strategy. You're just not using it with a quadratic anymore. It's mainly the same structure. You'll just have to do like a full factor by grouping approach. So kind of neither here nor there. But let's maybe try a temporary change of variables. Let's introduce a new variable named, I don't know, u. Could be anything you want. Let's say that u is x to the second. Just by definition, we just arbitrarily choose that, right? There's a reason I chose that variable. If you look at x to the fourth as like x squared times x squared, then if u is x to the second, x to the fourth is like u times u, which is u squared again. That's quadratic, right? If you look at the middle term for negative 3x squared, well, if u is x squared, then that looks like negative 3u. So by choosing a variable to represent another squared, you can take this fourth degree, second degree constant pattern, and you can maybe make it look a little more familiar to where now it's u to the second minus 3u minus 10. That's definitely a quadratic. That's ripe for factoring with the AAC method. That's going to feel very, very familiar based off of what we saw in Unit 3. Some people really like this approach. Some people hate it. Now, if I want to finish this out and really find my answer, I'm going to factor that polynomial in u, but I can't forget that I'm not really dealing with u, right? I'm going to have to put x squared back into the problem. I'm just going to do it later. If I'm looking at u to the second minus 3u minus 10, I'm going to notice that factors with the AC method, and I'm looking for factors that multiply to -10 that add or subtract to -3. That's going to be -5 and +2. I can take the shortcut here because the a term in front of u to the second is just a 1. So I'm just going to jump right to it, right? U squared minus 3u minus 10 is the same thing as u minus 5 times u plus 2. That's factored. It's good to go. Here's where I put back the thing that I substituted out. I just said arbitrarily that u is equal to x to the second. I'm not really solving a problem for u. I'm trying to solve a problem for x. So anywhere I see a u at this stage, I'm going to put the x squared back into the problem. So if u squared minus 3u minus 10 factors this way, x to the fourth minus 3x squared minus 10 is going to factor a similar way. It's just everywhere I saw a u, there's now an x to the second. And you'll notice that I'm putting that extra factor that I took off at the beginning back into play. I don't want to forget that term. It's definitely going to yield a solution. If I forget that it's there, I'm going to lose a root, and the fundamental theorem of algebra is going to be looking like it's broken, right? I don't want to do that. Now, this is where I can use the zero product property. I can say that 0 is equal to x times x squared minus 5 times x squared plus 2. Even if I tell you that I'm taking like 3 numbers in my head and multiplying them together to be nothing, and I'm telling you nothing else about them, right? It doesn't really matter how many I give you. If they're all a product and they're all equaling 0, then at least one of them is 0, potentially all 3 of them, right? It's just a natural extension of what we saw with quadratics up to like cubics, quartics, and quintics. So if I've got this times this times this, these complicated factors that are equal to 0, well, the first one's going to say, well, either x is 0, and that's kind of by default automatically solved, right? Or maybe it's x squared minus 5 that's equal to 0. And if that's a factor equal to 0, then I add the 5 and I take the square root, so I get 2 real solutions out of that, albeit not very pretty ones. And then I got to deal with my last one, right? If x squared plus 2 is equal to 0, then I can subtract the 2 and take the square root, but then I'm going to get some imaginary roots out of this. Now, as a sanity check, let's count up the number of distinct roots that we have, compare against the degree of the polynomial, right? I started with a 5th degree polynomial, so I expect 5 solutions. They can be real, they can be imaginary, but I need 5 of them. I see that x equals 0 is a root, plus minus root 5 are roots, and then plus minus root 2i are roots. That's all 5 solutions, so I know I've captured every single one of them. Nothing is missing. What I want to do is maybe show you guys graphically how to confirm that those really are the real roots and that this actually works. The graphical approach is maybe not so good in the sense that you wouldn't be able to find those imaginary solutions, but you can use it to check the real ones. I'm going to pull that up here in just a minute. We'll sort of correlate and see what we got. All right, so I've jumped gears and moved over here to Desmos. Notice that I've got my green function going, and that's the x to the 5th minus 3x to the 3rd minus 10x function, right? It's a pretty complicated, wiggly looking function. It's got a lot of interesting behaviors that make it kind of distinctly different than just x to the 5th or even just x to the 3rd, right? But what I want are the places where it's crossing the x-axis, where it's going to give me that y value of 0. And as I zoom closer into the x-axis, I see that I'm going to have 3 distinct roots that I can pin down. Nice thing about Desmos is you can kind of click on those points and it will tell you exactly where they are. You can do this with a graphing calculator. You'll just need like y equals 0 as a second function, and you're going to go second trace to the calc menu and go option 5 for intersect, but you can confirm it either way. Now, notice here that I've got 3 real roots. One of them is nothing, and the other one is plus minus the square root of 5, this crazy looking decimal that's about 2.236. Now, again, if I wanted to capture the imaginary solutions, I would need a 3-dimensional graph where part of this is going to go into the screen and out of the screen. That's well beyond the scope of what we're trying to do graphically on a high school level. That's not to say that I don't think that there's ways to do it, especially on the internet. I'm sure some crazy person has come up with a way to visualize that. It's really cool, but it maybe is a bit much for what we're trying to do. Algebraically, you should be able to find all the roots, regardless of whether they're imaginary, complex, or real. This graphical strategy is intensely useful if you're trying to find the real roots. So I would strongly recommend using it to verify that you're on the right track, especially as you go with factoring. But bear in mind that you're going to have to do a little more legwork to make sure that you're capturing some of the other values as well. So I'm going to go to our last example. here in our time for our notes today. This one I think is maybe the trickiest one of the bunch. This one is, I think, on the very end of the notes. It's this random function, f of x equals x to the third minus 8. It's a cubic function, so I would be not terribly surprised to believe that I should get three solutions out of it, right? Something kind of weird happens, though, as you're trying to pin them down. Now, if I've got one variable to the third, minus 8, and I set my function equal to 0, it's really tempting here to just add the 8 over, so you got 8 equals x to the third, and take the cube root of both sides to get x equals 2. That really is one of the roots of the function. The only problem with that is that we should get 3. So 2 of them are unaccounted for. And a lot of students are going to ask, well, how on earth are you supposed to track those down algebraically? Now, this one is kind of an interesting factoring strategy. You'll notice that it has two terms with a difference, but it's not necessarily a difference of perfect squares. X to the third is not something times itself, and 8 is not something times itself. But if you look at each of those terms, it could be written as something times itself times itself. X to the third is what we call a perfect cube, and so is 8. So in some rare instances, you may find yourself in a scenario where you've got the sum or the difference of two terms that are perfect cubes. This isn't very common, but it can happen. There's a formula for how to work the factorization of these guys when you detect that there's a sum or difference of perfect cubes. If you have a difference of perfect cubes, so if you got like a to the third minus b to the third, you got to be careful because there's one version of this formula that's very different if you have a sum of perfect cubes, a to the third plus b to the third. What you'll notice for the difference of perfect cubes is that your first factor is a minus b, but then your secondary factor, the quadratic one to the right of it, is a squared plus ab plus b squared. It's similar, but slightly different for the sum. For the sum of perfect cubes, you start with a plus b, and then you go a squared minus ab plus b squared. This is kind of an oddball. And when I come back, I'm going to try and justify like where on earth this comes from and why it works. As maybe an initial exercise in showing that this really does work. Try multiplying the right-hand side of the equation back together and see what you get. You'll be able to show that this actually does work. Demonstrating why we break it down this way and then carry it out further is maybe something outside the scope of what we're seeing today. Might require the rational root theorem and some synthetic division to sort of prove it out. And we'll get there eventually. Now, for our time today, we just want to apply the formula. If I see x to the third minus 8, I know x to the third is x times x times x. If I see 8, it's 2 times 2 times 2. So I'm going to use that difference of perfect cubes formula. And everywhere I see an a, I'm going to write x. Everywhere I see b, I'm going to write 2. So you'll notice that I get this factorization, x minus 2 times x squared plus 2x plus 4. The thing inside parentheses is a quadratic with 3 terms. So I want to try and factor it further using the AC method. What you're going to notice there is that you need the factors of 4 that add or subtract together to get 2. And there's nothing that's going to work. It can't be 1 and 4, and it can't be 2 and 2. So the thing that's left over on the right turns out to be unfactorable. So I would say this is kind of like the piece de resistance, right? This is like the big culmination of everything that we've seen so far. I can use the zero product property with these factors to say, well, if x minus 2 is equal to 0, my first root really is 2, but I've got to go get the other 2 roots, right? And that's where I'm going to focus on the quadratic side of the problem. Now, if I can't factor and solve it, maybe I try graphing. You'll notice with x squared plus 2x plus 4, it doesn't hit the x-axis, which means your answers are going to come out either imaginary or complex. So to catch those, you need the quadratic formula. Now, I'm going to use the quadratic formula here, step by step, to try and reduce this down and figure out the exact nature of these 2 remaining solutions that I should be getting from my original cubic. I've got negative 2 plus or minus the square root of b squared minus 4ac all over 2a. I'm going to simplify. And what I get there is negative 2 plus or minus the root of negative 12. There's the imaginary component, right? That's why you don't see them. via graphing or any sort of factoring method. Now, the root of negative 12 I know is going to give me imaginary answers, so usually what I do first is I ignore the negative, but I write an I next to the root 12. So now I can say, okay, root 12 is kind of the same thing as root 4, root 3. If I rewrite root 12 as root 4, root 3, then root 4 looks like plus minus 2. And then I've got the root 3 that I can't do anything with. So I'm just simplifying radicals there. Now, the negative 2 and the 2 in front of the radical can both be equally divided by 2 with no remainders. So as I'm working, I'm kind of slowly condensing and simplifying and cleaning things up a bit. And then I get my two complex solutions, right? I get negative 1 plus root 3i and negative 1 minus root 3i. You would never know that those are roots to this function if you were just looking at the graph, because the graph doesn't capture complex and imaginary numbers, right? You need a third dimension to the number system in that approach in order to find these. So if you're looking for them algebraically, and you know there's three of them and you're only getting the one, remember that when you see these scenarios, either it's a multiplicity issue, so the real thing shows up multiple times, or the others are imaginary. And when they're imaginary, remember from unit 3, they come in pairs because it's a root of a negative and you always got to do plus minus. Lots of stuff to unpack here, right? Lots of different starts, lots of different variations, examples. We talked about multiplicity. We talked about some factoring strategies. We talked about how to verify real solutions versus graphical solutions. There's a lot to unpack here. So definitely a day that I wish I was there in class with you guys to kind of work with you guys side by side on some of these practice problems. When I'm feeling better, and I'm hoping I'm feeling better soon, we're going to kind of work a few more of these as warm-ups just to make sure that everyone's on the same page. In the meantime, I want you to get a start on practice 4.2. As we start heading into next week, which is Thanksgiving week, we're going to have kind of a weird split on that Tuesday. So we're going to call the soft deadline on this the 1st and the 2nd of December, and we'll pick up as we go along. Other than that, though, I hope you guys enjoy the rest of your day today. I will see you guys again, hopefully very, very soon. In the meantime, take care. Have a good one.